Okay, so this class we will discuss on how we can do the DC analysis. So for this course, we will use the Mosfet for the amplifier application. So this is similar to what we have done in the BJT chapter. So the difference is instead of BJT, we are using the Mosfet. And then for this course, we only focus on EMOSFET and mainly using the N channel. Okay, so this is the revision on what we have learned in the previous class. So for the EMOSFET, E stands for enhancement. So enhancement MOSFET can be divided into two types. The first type is the N channel EMOSFET, and the second type is P channel EMOSFET. What is N channel EMOSFET? The EMOSFET, the N channel here, the naming of the N channel referring to the N here is negative. This is electron as the channel. So the EMOSFET create the electron channel by inducing create or induce the electron channel by applying the positive voltage at the gate. So this is positive VG. Okay. So and then for the in terms of the structure, the EMOSFET is made from the P-type silicon substrate. So the substrate, the base is the P-type silicon. So the electron, the minority carrier, minority electron inside the P-type silicon will be attracted by the positive gate voltage and induce the electron channel. This is the N-channel EMOSFET. Okay, on other hand, the P channel is the P here is positive referring to the hole. So for this we are inducing the hole channel inside the N-type silicon substrate. So for the MOSFET, the general operation is we induce the channel that made from the minority carrier inside the substrate. Okay. So and then for the EMOSFET, this is normally off. So you need to apply something to turn on the MOSFET. Okay. And then the below diagram is the symbol of the MOSFET, the N channel. This is N channel and this is the P channel. So to differentiate between the EMOSFET and with other type of MOSFET, for the EMOSFET, you see here we have the dash line here. So dash line indicate that there is no physical channel connecting the drain and the source. So you need to apply the voltage at the gate in order to connect the drain and the source. So this is the dash line mean. Okay, and then to distinguish between the N channel and P channel, you see the arrow here. So the N channel pointing in, P channel pointing out. To distinguish between drain and the source will have the connection to this middle arrow. So this is the source. Okay. Previous class we have discussed on the current voltage characteristic of the MOSFET, of the EMOSFET. So the N channel EMOSFET, this is normally off. So means without any application of gate voltage, there is no electron channel and there is no current flow. So you need to apply positive gate in order to enable the current flow at the drain. So if we plot the drain current versus the gate voltage. So gate voltage is the control terminal, so control voltage. So when gate is 0, so when the gate is 0, current is 0, drain current is 0, and when gate is 1, is still 0. So the gate voltage need to be above a specific voltage value. We call it as a threshold voltage. This is a threshold voltage. Okay, in this case the threshold voltage is 2 volt. So above the 2 volt, the drain current start to flow. Okay, this this is called a transfer characteristic. Okay, this transfer characteristic can be mathematically expressed by this quadratic function. Okay, so we have the ID is equal to K times VGS minus VGSTH square. Okay, and take note that here VGSTH is a threshold voltage. So there is many way how we can denote this threshold voltage. Sometimes we use the word the symbol of VTH, sometimes VT, sometimes VGTH. So please take note if you refer to other references. So the way how they denote this threshold voltage may be different. Okay. So and then the K here is a constant that related to the device structure. So this is a constant. So usually usually the K will be given, but if the K is not given, they will provide the graph ID versus VGS graph, or the specification on ID on and VGS on. So what is ID on and VGS on? ID on and VGS on is any point where the transistor is in the on state. For example, if you take a look at this transfer characteristic, okay, you can pick any point. Let's say I pick this point. So this is where the VGS on is equal to 5 volt, and then the ID on will become 2.5 milliampere. So from these two value, you can calculate the K of the characteristic or the graph. So the K is 2.5 milli over 5 minus the threshold voltage is 2, so 2 square. So this calculation will give you 2.5 divided by 3 square is 9. So you will get 0.28 milli. So and then the unit for this K value is ampere per voltage square. Okay. So this is the transfer characteristic. So another point that need to be remember is the current relationship between the inside the transistor. So in general, the common direction for the current inside the transistor is the current gate is pointing in. So this is VG. Drain current is pointing towards the source. This is ID, and source current is exiting the transistor. However, for the current relationship between these three currents is the gate current is always 0. So why the gate current is always 0? Because between the gate terminal and the source and drain, it is isolated by an insulator inside the MOS structure. So we have oxide in the middle of between metal and semiconductor. We have oxide. So oxide will block the DC current. Oxide will block the DC current. So that's why the VG is always equal to 0. So when VG is always equal to 0, so KCL ID will equal to IS. Drain current will equal to source current. Okay, for this current symbol, so we can use ID. Usually we use the term ID, or sometimes you use the term IDS. So any symbol is okay. Okay, so as I mentioned earlier, we want to use the Mosfet as an amplifier. So similar to what we have done in the BJT, the transistor need to be biased at a very suitable operating region. So this is the output characteristic. This is the output characteristic of the Mosfet. Okay, so drain current versus VDS at a different value of VGS. Okay, so VGS here is a fixed value. but we vary it at certain condition. So if you see this output characteristic is very similar to the characteristic of BJT. So in the BJT you have the graph of IC versus VCE, okay, at IB. So this is the graph of BJT, and then the graph is similar, but the naming of the operation region is different. For example, the linear here, the BJT is called saturation, okay, and then the cutoff here where the current 0, this is same, we also call as a cutoff region. Okay, for the saturation region, for the BJT we call it active region. Okay. Okay, so if you consider the Mosfet output characteristic of the Mosfet, so this is linear, this is saturation, and this is cut off. So the suitable operating region for the amplifier application will be the saturation region. Okay, saturation region. Okay, and then in this output characteristic, there is another important parameter. We call it as VD set. VD saturation is the point where the VDS, where the voltage at the drain source, where the drain current start to saturate. So this is the point where the current start to saturate at a fixed value. So this is equal to VGS minus VT, VGSTH. Okay, so we need to make sure that the transistor is located or set in the suitable operating region. So how we can do that is by using the bias circuit. So bias circuit is a circuit configuration that set the Q point of the transistor at certain operating region. So we have many type of bias circuit. So two of them are, first is fixed bias circuit. Fixed bias circuit, you can use multiple DC source. For example, here we have two DC source, 40 volt and 10 volt. Okay, so the first, the 10 volt DC source is power the gate terminal. It's connected to the gate terminal, and the second power source is connected to the drain. Okay, or this is a common bias circuit for the MOSFET is voltage divider circuit. So this is also similar to the BJT chapter. So for the advantage of the voltage divider circuit is we only require only single DC source. So we only use the 40 volt DC source.